good morning, everyone. Happy Wednesday. So let's get started. Okay, so last time we were looking at method of proof for sets. Okay, so I kind of looked at some examples from section 4.1, but I want to spend the first part of today going through the examples in the lecture notes. I'll fill in some details. Okay, so there are several proof methods for sets. Basically are related to the proofs that we've done with the logic laws. Basically, we look at sets as they have elements, right? So, they're related to the preposition that we've done before, is because we can sort of look at is this an element of the set or is it not an element of the set, and those form prepositions, and you can use the laws of logic, those prepositions, to prove things about sets. Okay? So we looked at example 1, sort of proving something is not equal by finding one counterexample. But counterexamples don't work if you're trying to prove equalities, because you want to prove that things, two sets are equal to each other in general. One example is not sufficient. You want to have a more general proof that shows that it's true for everything. All right, and Venn diagrams are useful, just kind of drawing pictures and showing that the shading is the same. And we looked at proof by membership tables, which is basically making a truth table similar to what we've done before with prepositions. Okay, so let me look at this example. I don't think I looked at this example previously. All right, so this example says that we want to prove basically the distribution law, right? So A united with the intersection of B and C is A united B intersected A united C. So it's kind of, notice it's like a distribution law for prepositions, but not with sets. Okay, so I want to do it a couple of ways. I want to do it with a membership table, and also want to do it with Venn diagrams to see how it works both ways. All right, so let's do the truth table method. Actually, let me see if I can insert a table in here, kind of keep myself a little bit more organized. So I have 3 sets. So I want to start with, let's see. So I have set A and set B and set C. All right. Cool. So I'm going to need 1, 2, 3, 4, 5, 6, 7. I need one more row. There we go. Okay. So just like truth tables, we want to use ones and zeros, true and false. Okay. So I have my choices for first set, the ones and the zeros. Yes, that's my dog. And for B, the ones and the zeros. Okay, and for C, okay. All right, so in terms of sets, a 1 means that an arbitrary element is a member of A, and a 0 means an arbitrary element is not a member of A. So again, you can think of them as propositions, because you're looking, a proposition is this element a member of the set, or is it not a member of the set? So basically you can change kind of, or think of sets as prepositions, just like we were doing with the laws of logic. All right, so now we want to see if they're equivalent. Basically, they're equal, we want to see if these both sides of the equations are equivalent to each other. So we want to build up to get a column for the left-hand side and the right-hand side. And if they have the same entries in the membership table and the truth table, then they're going to be the same. Okay, so let's make a few columns here. Let's add a couple of columns. So first I want B intersects C in here. Okay. So if I'm doing the intersection B and C, I get 1, 0, 0, 0, 1, 0, 0, 0. Okay. So basically, as I said, if an element is a member of both sets, it's going to be in the intersection. So the only time you get a 1 for the intersection is when they're both 1s. So same rules as regular truth tables. All right, now let's do a column with the whole thing. Okay, so now I'm going to take A union with B intersects C. All right, so I'm going to get 1, 1, 1, 1, 1, 0, 0, 0. All right, good. So this is one side of the inequality there. Then we're going to work on the other side. Okay, so let's get a few more rows in here. I think I need 3 of them. Okay, so let's do A union B in here. Okay, so this is going to give me 1, 1, 1, 1, 0. Nope, that's a 1. 0, 0. Let's just check. So yeah, okay, cool. Okay, and then let's do the union of A and C. Okay, so this is 1, 1, 1, 1, and 1, 0, 1, 0. Okay, and now I'm going to do the intersection of these. Put these together. All right, so this is the intersection. It's the red. So 1, 1, 1, 1, 1, and then 0, 0, 0. Okay, now we're gonna match. See these columns, right? They match. That means that they're equal, they're equivalent to each other. Okay, so basically it says that if an element is a member of this set, A union B intersects C, it's also going to be a member of this other set. And if it's not a member of this, it's not a member of that. So because they match perfectly, then those sets must be equal to each other. All right. Okay, any questions so far for this proof with membership tables? We're good? All right, let me just check the message board. All right, cool. Now let's do this also with Venn diagrams, see how that works. All right, so with Venn diagrams, we draw some pictures. Okay, so we're going to have a picture for one side and a picture for another. Okay, so we have 3 sets here, A and B and C. Okay, and on one side I want to show A united with B intersects C. Okay, so let's draw B intersects C first. Let's see. So B intersects C is in here. Okay. And then if I want A united with B intersect C, then it's going to be everything in A and everything in B and C. So it's going to be this set right here. Okay, so all the shaded area represents A union B intersect C. Okay, now let's work on the other side. Okay, so on the other side, we want A united B intersect with A united C. So we're going to draw a different one. So let's draw our three sets again, A and B and C. So let's do A union B. So A union B is this part right here. All right. And then let's do A union C. I'm going to do it on a different picture so it doesn't get too messy. All right, so let's do green. A union C is this part right here. All right, now I want the intersection of these. So you're gonna have to imagine grabbing this and putting on top of that. And we can see what areas are shaded that are the same. And you can see that all of A is shaded in both of them. And then the other common part is this sliver right here. Right, this sliver right here between this sliver right here. It's also this sliver right here. That's also common to both of them. So when we put them on top of each other, then it's going to give us the same picture as before. Okay, so A and B and C. Okay, so the intersection between the two pictures above is all of A. It's all common, and this sliver right here between B and C. Okay, so this is A united with B and A united with C. And what's common? The intersection between the two of them. So because the two pictures match, that's a Venn diagram proof. Okay. All right. Any questions with that problem? I'm trying not to lose all the notes that I give. Okay, there we go. Okay, so often you have a choice, right? When you're asked how to prove things about sets, there are choices in how to prove things. Okay, so we've seen Venn diagrams, we've seen membership tables. Okay, so and often you can prove them more than one way. Sometimes one way is more appropriate than another, but it's often personal choice, whichever you like. As with propositions, Venn diagrams and membership tables are kind of restricted to fewer sets. Like if you have more than three sets, both of them are a bit awkward to do. So it's good to develop other rules that can sort of take care of more complex situations, right? So this is where kind of the proof by definitions come in, right? It's definitely the most formal way to prove things with sets, but it's probably the most versatile. And what we're going to do in section 4.2 is probably the most convenient way to do proofs of sets. Okay, so let's look at proofs by definitions. We haven't looked at these yet, right? So proofs by definition, basically, we look at the definition of what set equality is. Okay, so the definition of set equality. So this says that if two sets are equal to each other, or it says that set A is equal to set B, if A is a subset of B, and also B is a subset of A. Okay, so it kind of have to go both ways, right? So let's see. So if A is a subset of B, should probably just draw it by hand. There we go. And if B is a subset of A. Okay, so that's what set equality means. Also means that they have exactly the same members. Okay, so basically, in order to prove these with definitions, I need to do a if and only if statement. I need to prove that A is a subset of B and B is a subset of A. Okay, so you start with the assumption, you're going to assume that X is a member of the first set, and you're going to try to prove that that X is also a member of the second set, right? And then go the other way. Okay, so let's look here. So we're going to start with saying, let's say that X is a member of this set right here. Okay. All right, then we basically are going to try to change these statements to propositions and use propositional rules that we know in order to show that X is also a member of a set complement of A intersect to complement of B. All right, so if X is a member of the complement of this set, then that means that X is not a member of AUB. So if it's the complement, it's not going to be in the set itself. Okay. All right. So now if X is not a member of AUB, right, then basically that says that X is, it's not true that X is an AUB. Okay. So this means that it's not true that X is in A or that X is in B, because the union means that it's either one set or another. Okay, and basically I changed things from sets to propositions. So this is like a P or a Q, and I can use proposition rules and proposition laws to take care of this. Okay, so because I have a negative, I can distribute it. So this means is not true that X is in A, and it's not true that X is in B. Okay, well, if it's not true that X is in A, that means X is not in A and X is not in B. If it's X is not in A, that means X is in the complement of A and X is in the complement of B. Okay. And because this is an and right here, so if X is in both in the complement of A and in the complement of B, that means that X has to be in the intersection of the complements of A and complement of B. Okay, so basically I proved that if I take an arbitrary element X, which is in the first set, it also has to be in the second set. Okay, so basically that means that this first set is a subset of the second set. Okay, any element in the first set is also in the second set. That means the first is a subset of the other. All right, any questions so far? All right. Okay, so we're going to do the second part now. Okay, so we also need to turn it around and work the other way. Okay, so what this means is that I need to assume that X is a member of this set and follow similar steps to show that X is a member of first set. And then that will show that the second set is a subset of the first set. And then if they're subsets of each other, they have to be equal. Okay, so let's do that process. And often, most of the time, this is just kind of going through the step backwards. Okay, so if X is a member of the intersection here, then that would mean that X is in the complement of A and X is in the complement of B. It has to be in both, right? So that means X is not in A and X is not in B. So it's not true that X is in A and it's not true that X is in B. Okay, all right. So I can use De Morgan's law backwards to say that it's not true that X is in A or X is in B. So because De Morgan, it switches from an and to a or, right? So I'm going to make this into a union because the or means that X is in the union of A and B. So the negation says that X is not in the union of A and B, which means that X has to be in the complement of the union of A and B. All right, so I started with, let's have an arbitrary element, which is in the first set. Through these steps, I showed that it also has to be in the second set. That means that this is a subset of this, like that. Okay, so they're subsets of each other. So if those sets are subsets of each other, then by the definition of equality of sets, that means these two sets have to equal to each other.
All right, so section 4.2 is called laws of set theory, because in the last section we...
Is that me talking? Sorry, am I talking to myself? All right. Okay, so any questions with this? Let me grab this. All right, so this is proofs with definitions or proofs with or not membership tables, but basically you look at an element being a member of one set, showing it's also a member of the other. You also have to do the reverse because it's not guaranteed that if you show that one set is a subset of the other, then it's going to work the other way also. So you have to show both parts. So it's like an if and only if proof. And I know these are kind of the most, they're the most formal ones, like the most formal proofs as compared to the others. But kind of this, I don't know, they're preferred by mathematicians. All right, did I have a question from somebody? Let me know. Yeah, I can you speak up? I can't hear you very well.
Good morning.
Okay.
Let's see, when we were doing prepositions, it mentioned truth tables and subsets there. And it said basically if this truth table was a subset of this truth table, that meant P implied Q, there was a relationship there. Does that still apply with set theory? So if A was a subset of B, does that mean A implies B?
So right. So with when we were looking at the universal, and so the truth sets, right? I think you're referring to. Let me see if I can remember. Right. So we looked at if two sets, one set is a subset of the other. So the truth set of P is a subset of the truth set of Q, then P implies Q. Okay, I think that's what we're looking at before.
Yes. And does that translate to sets now? So if a set was, set A, does that mean set A implies B? Because then you could use a lot of preposition laws with set theory.
Yes.
Okay.
Yes.
Awesome.
So this definitely holds.
Thank you.
There, I think there will be a couple of examples today where we have to prove that something is a subset of the other, and this implication will be very helpful. Okay, so yeah, this definitely holds true. Yeah, if one set is a subset of the other, there's an implication that says that if X is a member of the first set, then it has to be a member of the second set. Okay, good observation. Any other questions? All right, let's see. Okay, so I think I did. Okay, I think I did 6. Yeah, let's look at 7. Okay, so yeah, 7 is a prove that one set is a subset of another. Okay, so with subset, with proving like if one set is a subset of the other, I think Venn diagrams are a bit tricky because I think they're sort of hard to draw to kind of show something is a subset of another. And membership tables don't work that great either. So these proofs by definition are often the most useful in proving that something is a subset of another. So let's look at this one. Okay. So basically to show that A intersect B intersect C is a subset of A intersect B, we want to show that if X is a member of the first set, then X will also be a member of the second set. Okay, so let's start. So here we only have to go one direction because we're not showing equality. We're just showing the one direction. Okay, so we're going to start with this as our premise. So X is a member of A intersect B intersect C, then that means that X is a member of A and X is a member of B and X is a member of C. So basically I have these, each of these in parentheses are like P, Q, and R. Okay, they're all prepositions. They're statements that can be true or false. Okay. All right. So because of the and, because this is a conjunction, I can separate it by conjunctive simplification. Okay, so if they're all stated, if they're all premises, then I can say that X is in A and X is in B. I can separate them out. Okay, all right, so if X is in A and X is in B, then this means that X is in A intersect B. Okay, so that's it. So basically that's the end of the proof because I showed that something that's a member of the first set has to be in the second set. So that means that this first set right here is a subset of this set right here. Okay. All right, any questions with this one? Oops. Oh, I went in the wrong place. There we go. Okay. So let me save this. Okay. I know this is being recorded, but sometimes watching a whole Zoom session is not so much fun. So I'm trying to save these as I'm lecturing and post them in Canvas if you want to read back through the notes. Okay. All right, so let's look at section 4.2 now. Let me share that document. And this is called Laws of Set Theory. Okay, so this is like the final way of sort of showing, proving things about sets. That's set equality in particular, but also showing things are subsets of one another. And if you look at this table, it's very similar to the laws of logic with the propositions, because as I said, sets and propositions are very much related to each other. You have your commutative laws, distributive laws, identity, complement, idempotent, null laws, absorptions, De Morgan's laws, and involution. So they're very, very much copies of the ones with the P's and Q's. Okay. I noticed that there's not that part at the bottom with the implication laws, but once we kind of change our set notation into propositions, those also kick in. So we can use those laws also. So this is probably my favorite way of proving set equalities because it's a bit cleaner than the definitions, like with X is showing the one is a subset of the other and vice versa. It's kind of a bit of a pain. So if we kind of use known laws, then it makes it a bit shorter and a bit cleaner. Okay, so let's look at some of these examples. So the first one, prove that the complement of A union B intersects C is the same as the union of the complement of C with the complement of B intersected with the complement of A. Okay, so just like in trig, we basically, when we're trying to prove an identity and equality, you want to start with the more complicated side and transform it into the less complicated side. Okay, and just like proofs in trig, you're not really allowed to cross over the equal sign. You're not allowed to sort of do things to both sides of the equation. Right? You're also kind of encouraged not to work in parallel. Basically, you want to start with one side and transform it into the other. Okay, so that's kind of the standard way of doing it. Okay, so I'm gonna say the more complicated side is this one. Okay, they kind of look the same, but let's say this is the more complicated side. Right. So I have a complement. Right, I'm taking a complement of this thing right here, and De Morgan law is great with complements. Okay, so a complement over a union, because I have my union here, it's basically this set union that set is going to make this complement of A intersect complement of that parentheses. All right, so this is De Morgan's. Okay, now I can apply the complement here with De Morgan's law again. Okay, so complement of A, and then complement of B union complement of C. Again, I applied De Morgan. Basically, we can see that we arrived at this. It's out of order, but the commutative laws allows us to switch the order of the union and of the intersection. Doesn't allow us to switch like the order if there's intersection and union, but within each. So like within the parentheses, I can switch the order of the complement C, complement B. And out here, I can switch the order of the things that are intersected with each other. Okay, I couldn't put like A in parentheses and take B out of the parentheses because that would be distributive law, but I can switch the order within of the elements of the union of the elements of the intersection. So those are commutative. All right, so is this table something you can print? So yes, this is in the lecture notes in Canvas. So if you go to Canvas under this chapter and look at the section 4.2 lesson PDF, then this is, the table is there. Okay. All right, so that's the proof for this example. Any questions with this? Okay, all right, so it's very similar to doing things, proofs of propositions that we were doing before. Okay. All right, let's look at another one. All right, so we're gonna prove this statement right here. So definitely I would say the more complicated side is the left-hand side. So let's start with that one. So I have A intersect B and A intersect BC, and I want to transform that into A. All right, so if I look at my laws above, I have A intersect something, union, A intersect something else. Let's see if this is similar to any rules here. Okay, anybody see anything that we can use to simplify that or to rewrite it? Okay. I see the distributive laws, right? The distributive laws might be useful here. So it looks like, yeah, it looks like this side, right? So A intersect B united with A intersect C, you can compress it. It's like factoring out the A. You can compress it into this, okay? All right. So this is going to compress into A intersect B united with BC. Okay, this is distributive. Okay, and then this right here is a law. Okay, so that says if I take a set and I unite it with the complement of itself, that's going to be the universal set. Okay, and this one is number 5, the complement law. Oops. Okay, and there's a law that says if I take the intersection of a set with the universe, then I get the set itself. Okay, so we can look that one up too. I think that one is number 4, the identity law. Okay, and that's it. Basically, just sort of use those well-known laws of distribution, identity, commutative distributions, complement laws, and it makes it like a lot neater. All right, any questions with that example? Okay, let me just paste this in here. Okay, so now let's look at this one, which is proving things like subsets. Okay, so let's see how we can phrase this one. Okay, and this is like you said, a subset leads to an implication, and we can again think of things as propositions. So we're given that A is a subset of B. Okay, so this basically means that if X is a member of A, then that implies that X is going to be a member of B. So what I have here is a if P then Q statement. Okay, so P is the statement that X is a member of A, and Q is the statement that X is a member of B. Okay. So now we're told that A intersects C is not the null set. Okay. So what this means, so if A intersects C is not the null set, this means that there must be an element inside A intersect C. Okay, so X is in A intersect C. Okay, so these are like two separate statements right here. All right, so A intersect C is not the null set, then that means there has to be an element in A intersect C, which means that X is in A and X is in C. All right. Well, I know from the first premise right here that if X is in A, then X has to be in B. So this right here says that if X is in A, then this X has to be in B. And I know X is in C. Right? So basically, I kind of used the detachment here, right? Because I have if P then Q, and I know P, then Q must be true. So we're basically using detachment, the law of detachment, right? So if X is in B and X is in C, that means that X has to be in the intersection of the two sets. And that means that the intersection of these two sets is not empty because it has a member in it. Okay, so this is kind of very much like we're working with sets, but we're really using the preposition or logic laws, the implication and the law of detachment and conjunctive simplification and all that stuff we were using before. All right, any questions with this one? Okay. All right, let's look at this last one. Okay, so this one has subtraction in it. So I want to prove that A united B minus C is A united B minus C minus A. Okay, so first let's remember what subtraction of sets means. So if I have something like C minus A, so C minus A means that I'm looking at all the elements that are in C but not in A. Okay, so X is in C but not in A. Okay, so I think we've seen this sort of equality before. So this means that it's in C but not in A. Okay, so C minus A means the same thing as the intersection of C with the complement of A. Okay, so in order to use the laws in the table, none of them had like subtraction in it. We want to change any subtractions into in intersections, and then we can use things like commutative, distributive, De Morgan's law, etc. Okay, so I'm going to start with the more complicated side. So let's start with AUB minus C minus A. And change the subtractions into intersections. So first I'm going to work on that parentheses. So let's say this is A united B minus C intersect AC. Okay. Now there's another subtraction. So I can see that I have this minus that. So using the same definition, this is going to be the first set intersect with the complement of the second set, like this. Okay, all right. So now I'm going to apply De Morgan's law to this one. All right, so let's do De Morgan's law here to distribute that complement. So I have A united with B intersect complement of C united with A complement of its complement is just A itself. Okay, so now this looks like a distributive law again because it's A in both of them, A united with something and A united with something else. So this is going to be A united with B intersect complement of C. So that's the distributive law. Okay, so now if I compare to, I'm trying to get here, right? I can see that this A united thing is already there, but I want to change this back into a subtraction, okay? So by the subtraction definition, you see B and not in C, this is basically just B minus C, okay? So it matches, that's the same thing. Okay. Okay, any questions with that problem? Just let's see what the question is. So proofs for this chapter aren't so formal. We don't need the number of steps list the law at every step. Yeah, I think sort of I showed you guys sort of the very formal process of proofs by proposition. But like in practice, when you prove things, they look more like this. You can still give justification if you want, but I'm not gonna expect the justification at each step anymore, as long as it's sort of clear what you're doing from one step to the other. Then you don't need to say De Morgan's and distributive and identity like at every step. That's I thought that's kind of that's a really awkward way of proving things. So a bit less formal from now on. Cool. Any other questions? Okay. So let me go to, I had a question earlier to look at problem 1 in quiz 7. So let me bring that up before I start a new section. All right, so let me stop sharing for a second. All right. Let me see if I can find quiz 7. Okay, need to go to Canvas and open it. Quiz 7. There it is. All right. Can I give an example of problem 1 in quiz 7? Okay. So let's see. So this problem says, so C means that X is cold-blooded. F means X is a fish. S means X lives in the sea. So translate into a formula. Every fish is cold-blooded. All right, anybody tackle that one? So every fish is cold-blooded. I'm going to need to use the universal, right? So you go every X such that CX. Oh, every fish. Ah, yeah. I guess I'm assuming X is in a fish, but yeah, you're right. I think I skipped a step there. So yeah, basically, for every X, if that X is a fish, then it's cold-blooded. Yeah, that's better. Okay. So basically, it's X could be any creature. And this says that if X for every creature, if that creature is a fish, then it's cold-blooded, and that translates to every fish is cold-blooded. Okay, let's see what B says. So B right here says there exists an X such that SX and not FX. Okay, so what does that say? So there is a creature. So that lives in the sea. And is not a fish. Okay, or in other words, they are non-fish creatures in the sea. I don't know how you translate it grammatically well in English, but that's what it means. There are creatures in the sea that are not fishes. Yes, so Yuval, that's correct. If we're talking about all, the universal thing, and you basically, you needed to be two things, then it's going to be a conditional statement. But if it's a existential, that there exists one, then it's going to be a conjunction. Yeah, so that's a really good observation. All right, and C. All right, so C is like every creature that is a fish. So if there is a fish, then it lives in the sea. So basically this says that every fish lives in the sea. Yeah, so basically for all creatures, if they're a fish, then it means that they live in the sea. Okay. All right, so that was number 1. Okay, so somebody had a question about the first problem on the quiz. So yeah, that's it. Okay, so yeah, the quiz is due tonight by midnight. That's fine. And it covered 3.8, 3.9, and 4.1. Okay, so they were the universal and existential statements. And let's see, let me just look through. some of the proofs that we did Monday. Okay, and then sort of the set theory stuff that we were doing today. So hopefully you got enough information from today to finish up those last few problems. All right, so let me see if I can help you with 8. So number 8 on the quiz. So use logic laws to show this. Okay, so basically I'm given prepositions here. Okay, so, and I'm trying to show, basically these are prepositions. This is the first premise. Okay, so this is the first premise, second premise, third premise, fourth premise, and this is the conclusion. Okay, so I'm trying to show that these 4 premises lead us to that conclusion. Okay, so this is a little bit like a combination of what we know about the sort of universal and existential, and also with the logic laws that we've been using. Okay, so let's see. I want to, let's see, look at the time. Okay, I think this might take a little bit longer to explain. So let me leave it till the end of class, and if you have time for office hours, then I can go over it. Okay. Again, I'm sort of, let me see how if I can explain 6b quickly, then I will, but otherwise I will. Okay, yeah, I think I can go through 6b fairly quick. All right, so 6b says simplify the statement below so that the negation symbols occur only directly next to predicates. Okay, so B says this. So yeah, we need to distribute the negation, but it's like, how do you distribute a negation to an implication? All right, so let's kind of look at a simpler statement. Consider this to be like, this is P and this is Q, right? So to distribute the negation to an implication, we don't know how to do it directly, but we know that we can change the implication to a disjunction, all right? And once you change it to the disjunction, then you can do it De Morgan's law. Okay, so you're going to have not P and not Q. All right, so basically this is what you're doing here. So we're going to change that implication to not this or that. Okay, then you distribute the negation to here. So we're going to have, there exists an x such as px and not for all y py. Okay, and then this stays the way it is, but this negation goes through the universal sign and it changes to an existential one, and the negation goes in front of the proposition. Okay, so you can leave it like this, or if you want to change it back to a conditional, we can do De Morgan's law in reverse. We could say, I think that's probably enough. I don't think we need to. I think we could probably take out a negative, but I don't think that will probably just lead us back to here. So yeah, this is what we need. All right, so question, can we say that the universal quantifier implies the existential quantifier? We, like if I have this this is going to imply that. Yes, we can say that because this says for all x, p of x is true. So this will imply that there exists an x such that p of x is true, because p of x is true for all x, is certainly going to be true for a particular x. So yeah, that implication is true. Okay. All right, I'm going to stop here with quiz questions. And again, if you have more, then let me know during office hours. I want to start on the next section. All right, so let me share. Okay, Canvas. All right, so yeah, quiz 7 is due tonight, and writing assignment 4 is due Friday night, okay? I also put quiz 8 up, which is due next week, next Wednesday. So you can start looking at that and working on that over after today. And I also put up investigation 6, which is due not April 6th. I need to change the date on that. Yeah, it's not due April 6th. It's going to be due probably in about a week and a half. So I'll change that soon. I'm not sure how that got there. Yeah, so actually, let's see if I can change that now. As you guys have noticed, I'm not very good with putting the right due dates on stuff. Let's see, I think I want to make that due, the quiz is due here. Yeah, 13th. Let's do that. April 13th. So this one, this investigation 6 is worth more points than the usual ones. Usually it's worth 5 points. This is worth 10. It's a little bit more complex. So I'll have a look at it soon, because there's, I think there's kind of more going on there. So yeah, I have a look at investigation 6 also over the weekend. And you guys can collaborate on that. If you can sort of figure out how to communicate with each other, that would be great. So you can come up with strategies, like if you are in touch with the people that you sort of been working with in class usually, then that would be great to work with each other. But you can, if you can each individually submit a copy, that will make it easier for me to grade. Okay. All right, let's look at the next section. All right, so we're done with sets. Well, you're not done yet because you still need to do the quiz, but I'm done talking about sets for now. And we're going to start a chapter on number theory, okay? So as I said, we're in the second part of the course. And the first part, we kind of build these sort of tools, especially we looked at what sets are, and but the sort of the structure for logic and doing proofs. And then in the second half, we're going to kind of look at different topics where proofs are a part of them, like all the logic and the proofs are weaved into it. But we're kind of basically going to look more like at sort of applications of, of things, rather than sort of the very abstract stuff. It's still abstract, and we're still going to do a lot of proofs, but we kind of have the tools to do it now. So this first chapter is number theory. Then we're going to look at relations and functions. Then we're going to look at sequences and algorithms, and graph theory. So kind of more like computer science-y related things. All right. So this number theory, we're going to talk a lot about divisibility and modular arithmetic. And these are very, very useful in computer science, in particular when it has to do with things like cryptography. So, well, like nowadays we live in a day and age where everything, you have to have a password for everything, right? Because it protects your information, your grades, your financial information, your health information, everywhere that you go, you have a password. So in order to keep those passwords secure, then there needs to be a lot of programming to make sure that the passwords are secure. So that cryptography stuff is really essential to today's life. So a lot of cryptography is done with using really large prime numbers. And in order for computers to be able to do calculations with really large numbers, so for them to be efficient, there are certain algorithms that they need to use to make it efficient, so it doesn't take lots of computing time and power and resources. So that's this is building up to doing or learning how some of that math is done. Okay. So the first couple of sections in this chapter, we're kind of building notation and certain rules for arithmetic and theorems that will help us have the building blocks for doing those, knowing how to do those calculations. All right, so we're first going to talk about division. Okay, so we know what division is. So we're going to learn a bit of language and relationships in a format that you might not have seen before. So if we have a and b are integers, with a is not equal to 0, we say that a divides b if there's an integer c such that b equals ac. Okay, so a divides b means that a is a factor or divisor of b, or that b is a multiple of a. So basically we're looking at integers that divide into each other exactly, and there's no remainder. If a divides b, there's not going to be a remainder to the division, right? So this is sort of symbol that says, so a divides b, this vertical bar right here, which is basically the opposite of the fraction. Right? If I go b divided by a divides b. Okay, so this is kind of different notation that we're used to with the fraction. It's kind of reverse, right? And if a does not divide b, then you have like the slash with, so this says a does not divide b. All right, so let's look at these. So part A, does 4 divide 20? Okay, so I go, yes, 4 divides 20 because I can write 20 as 4 times an integer. Okay, so basically we're taking this as the definition of a divides b. A divides b if b can be written as a times an integer. All right, does 20 divide 4? And you're going to say no, because I cannot write 4 as 20 times an integer. I can write 4 as 20 times 1 over 5, but this is not an integer. So 20 does not divide 4. Okay, how about C? Does 0 divide 5? Can I write 5 as 0 times an integer? Okay. And the answer is no. Because 0 times any integer is going to give me 0. So that's never going to give me 5. It also breaks this condition right here that a can't be 0. Okay, so this is basically division by 0. All right. So let's see. Let's just save this. There we go. Let's not do that. Okay, so we're gonna prove a bunch of theorems. Like sort of, we're as I said, we're the stuff that we built over the first half of the semester. We're gonna use a lot. Okay, so anything sort of new that we're learning, there's gonna be some theorems to prove, and we're gonna use the methods that we learned along the way. Okay. But again, we're not going the very formal process. This is attachment. This is this. We're just going to try to construct a clear proof, but without the justification to all the steps. Okay. So this theorem says that if a and b and c are integers and a is not equal to 0, then these three, right? So the first one we're going to prove says that if a divides b and a divides c, then a divides b plus c. Okay, so these are my premises. All right, so I have premise 1 and premise 2, and I'm trying to show this conclusion. Okay, so let's do it with the direct proof. Okay, so direct proof means that I'm going to take my premises as true and try to build the conclusion from that. So we know first premise is that a divides b. And I know by the definition of divides, that means that b can be written as a times an integer. And I also know that a divides c. That means that c can be written as a times a different integer. You want to use different integers. If you use the same k, that will make b and c equal to each other, and that's a special case. You want to prove something for as general as possible. So we use different integers just to show that this would work for any number b and c. So k and l are different integers. All right, so these are sort of my premises, and I'm using the definition of divides by to write them like this. But I'm trying to get to here. I'm trying to get to a divides b plus c. Okay, so how do I get b plus c there? So to get b plus c, I need to add these. So I'm going to add the two equations, and I get b plus c is ak plus al. So this is going to be ak plus l. All right. So now I notice because k and l are integers, k plus l is going to be an integer. And because I can write this number as a times an integer, that means that a is going to divide b plus c. Yeah. So that's it. I got to the conclusion with a direct proof. All right. Any questions on how that happened on the steps? Okay. All right. Let's do this. The next part. The next part says that if a divides b, then a divides bc. So if a divides b, then a divides bc. Okay. So here's my premise, and I'm trying to basically show that this conclusion is correct. So direct proof again. So we're going to start with the premise, a divides b. We're going to use the definition of divides to say that b is going to be a times an integer. All right. And then we're going to try to figure out how do I transform this into my conclusion. So I noticed that in my conclusion, I have BC there. Okay? So what I'm going to do, I'm going to multiply both sides by C. Okay? So this leads me to BC is A times K times C. Let's put this together in parentheses. All right, so what do I have here? I have that BC equals A, and the thing in the parentheses is an integer. So this number BC can be written as A times an integer. That means that A divides BC. Okay, right? And that's it. We got to the conclusion. All right. Any questions with that one? Okay, now let's look at number 3. So if A divides B and B divides C, then A divides C. Notice it's like a chain rule thing, right? Okay, so I'll write it down here. So 3 says if A divides B and B divides C, then A divides C. All right, so I'm gonna let you guys play with this for 2 or 3 minutes. So try it out. And you want to start with your premises. So this is, I have premise 1 and premise 2. You take those as true and use the definition of divides by to write them as an equation. And then try to figure out how do I use those two equations together to get me the conclusion here. So this is my conclusion. All right, let's see what we got. Okay, so let's start with the first premise. So A divides B means that B can be written as A times an integer. B divides C means that C can be written as B times a different integer. Okay, so again, we know that KL are integers. All right, so I have these two equations right here. I'm trying to show that A divides C. So I want to connect A and C somehow. All right, so how did you guys figure out how can I combine these equations? Multiply? If I multiply CB, oh, that would be good. Or plug B into C. Yeah, multiplication would work too, right? If I multiply them, I would get BC is AB times KL, right? And because like B is not 0, then I can cross it out and I get C equals A KL, right? Or I could have plugged it in. I could have plugged this in for B and then get C equals AKL. Okay, so either way, we get to the same place. Right. So because KL is an integer, so this right here is an integer, C is A times an integer, that means that A divides C. Okay, good. Any questions with that one? All right. So so we're gonna look at a few theorems like this that sort of establish rules of manipulation or arithmetic with this divisibility stuff. Okay. So here we basically established it's like, yeah, if I have A divides into numbers, then here's how summation works. Here's how multiplication works. Here's a chain rule type thing. Okay. So basically we're building tools on how we can work with this divisibility. Oops. All right, and let me go over this next theorem. So this next theorem is a combination of the 1 and 2 above. So 1 and 2 above has to do with the sum and like a product. This is like combined. So basically it says if A divides B and A divides C, then A is going to divide into a linear combination of B and C. M and N are integers. So it's going to divide into M times B plus N times C, okay? So it's as you can see, it's like a combination of the addition and multiplication rules. All right, so let's start with our premises. So A divides B means B can be written as A times an integer. A divides C means C can be written as A times a different integer. And I'm trying to basically get to that expression somehow. So kind of combine these two premises, these two equations, so I can find that sum, right? So I see that I need, yeah, we're going to add them. But before we add them, I'm going to multiply this by M, so I can get MB. I'm going to multiply this by N, so I get NC. Okay, so multiply and add. So I'm going to get MB is AKM, and NC is ALN. Then add them. So I'm going to get MB plus NC is AKM plus LN. All right, don't really care what this is, except what I care about is that it's an integer. So because everything was integers, K and L and M and N, then that's going to be an integer. So because this number is A times an integer, then A is going to divide that number. Okay, so here I got to my proof. All right. Okay. All right, good. So I'm going to stop here. On Monday, we're going to continue with this section and go on to the next one, build up some more things about operations that we need for number theory, and that will lead us into doing modular arithmetic. Okay, so again, quiz 7 is due tonight, so stick around for office hours if you have questions, and I will try to help. Okay, otherwise, bye, have a nice weekend. You're welcome. All right, so I think Mike asked me about number 8 on the quiz, so I'm going to attempt to look at it. Well, I haven't looked at these problems for a while, so Mike, let's see how it works out. So I have these premises, and I'm trying to show this is true. Okay, so let's see if I can make sense of them. So I have P or Q, and not P. Okay, so let's put these together. So I said for all X, Px or Qx, and then I think this is going to be useful. And I know that there exists an X. So P of X is not true, okay? All right, so those are premises. And I'm actually going to write I'm going to take this negative out. So if I take the negative out, it's going to change it to a universal. Okay, so I'm going to write it like this. Okay, so I have, for all X, I have P of X or Q of X. And I know that it's not true that all of X, P of X. So this is like a conjunctive, disjunctive simplification, because I basically know that not P. So this means that for all X, QX. So this is disjunctive simplification. All right. Okay, now let's look at this here. Okay, so I have for all X, not Q or S. And this I'm going to change into a conditional. So this changes if Q then S. Okay, so this is the conditional equivalence. Okay, so now I'm going to combine like 3 and 4. So if I have for all X, Q, then S, and I know that for all X, Q of X, so basically I know the first one, then this implies that for all X, S of X. So this is detachment. Okay, so it works pretty much just like prepositions do, except that you have the universal and existential stuff there, but they basically work a very similar way. All right, so then I have this one. So for all X R, if R then not S, and I have that for all X S. So because this is like the negation, the opposite of that one, this is gonna lead me into for all X not R with indirect reasoning. Or I think it leads me into, it's not true that for all X we get R. I think that's how the indirect reasoning works. Okay, we have this is negated, then the first part is going to be negated. Okay, and then the negation of the universal statement is going to turn into the existential of the negation of R. That's by De Morgan's law. All right, so that's the conclusion that we're trying to get to. All right, so yeah, let me see. So for step 4 and 5, can we just do like step 2 and 3 instead? Oh, yeah, you can turn it into, I was doing it with conditional, but exactly, you can because you have not Q or S and you have Q, then that's going to give you S, right? And if you actually change this one into a or, right, because you have not R, not S and S, then that's going to give you not R. Yeah, so yeah, you could do like 2 or 3. I changed it to conditional, but you can do it with a conjunction there. Okay, no problem. Let me actually see how that works. All right, number 14. Let me pull that up. Ah, let's see about number 14. So number 14, use the following definition of absolute value to prove the given statements. Oh, yes, Tyler, this is office hours. If X is a real number, then the absolute value is defined by this. For any real number X, absolute value is bigger than or equal to 0. Moreover, X is absolute value of X is 0 implies X is 0. Okay. So this kind of lends itself to a proof by cases. Just because the absolute value, the way it's defined like one thing, one function for non-negative values and another functions for negative values. Okay, so let's consider case 1 when X is bigger than or equal to 0. Okay, so what I'm trying to prove is that the absolute value is always bigger than or equal to 0. Okay, so for X equals bigger than or equal to 0, the absolute value is defined as X. All right, so because X is bigger than or equal to 0, an absolute value equal to X, then absolute value of X is going to be equal to 0 for this case. Okay, now case 2, we're going to consider X is less than 0. So the absolute value is equal to negative X. But because X is negative, negative X is going to be positive, right? So in both cases, which covers all real numbers, we end up with the absolute value is bigger than 0. So that proves that part. All right. Now, if we want to show this, so moreover, absolute value is 0 implies X is 0. Okay, so let's see. So again, we go by cases. So for x is bigger than or equal to 0, if the absolute value of x is 0, is x. All right, so if the absolute value of x is 0, that means x equals to 0. Now, case 2 for this one, we can't really consider. I mean, we can look at it. It says for x is negative, absolute value of x is negative x, but this can't equal to 0 because that particular value is not allowed in the second part of the absolute value. So we just look at this part right here. All right, so because absolute value of x equals to x, if absolute value of x equals to 0, then x is going to equal to 0. All right, so that's like A. Okay, so we look at the different cases. Okay, any questions with that part? Okay. All right. Let's look at B. So again, we look by cases. So for any real numbers, absolute value of x times absolute value of y equals that. Again, we're going to look at cases like this. So we need to consider they're both positive, and we need to consider that x is positive, y is negative, x is negative, y is positive, and x is negative and y is negative. Right? So we consider all these cases. Right? So if they're both positive, then the absolute value of x times the absolute value of y is going to equal x times y. Right? And the absolute value of xy is going to equal x times y. And they're equal to each other. So we're good for that case. Second case, when x is positive, y is negative, absolute value of x is going to equal x. Absolute value of y is going to equal negative y. So if I multiply them together, this is negative xy. Right? Now, if I look at absolute value of xy, right? Now, if I'm doing absolute value of xy, if I multiply x is positive and y is negative, xy is going to be a negative number. So the absolute value of xy, according to the definition of the absolute value for negative numbers, this is going to be equal to negative xy. So you can see that they're equal to each other. So that works in that case. Right, so basically you go through each case of combinations and you're showing that this side equals to that side. Okay, so there's just lots of things to consider. All right, and for part C is very similar. You're doing X, Y's, all these 4 cases and showing that they're sort of, that's the way absolute value works. All right. So yeah, let me look at Cheyenne. Question 15. Okay, so let's look at question 15. I'm not going through all of question 15. Anyone in particular? That's a lot of parts there. I know I'm asking you to do it, but all right, maybe let's look at A. So if A is a subset of B and B is a subset of C, then A is a subset of C, okay? So if A is a subset of C, that means that if X is an element of A, then X is going to be an element in C. So that's kind of the definition of subsets. All right, And then it says if B is a subset of C. So that means that if X is an element in B, then X is going to be an element in C. Oh, wait. Sorry. If A is a subset of B and B is, okay. So A is a subset of B, that means if X is in A, then X is also going to be in B. All right. And if X is in B, then X is, okay. So notice that basically I changed these subset statements into prepositions. Okay. So this is like if P then Q and if Q then R. Right. So by the chain rule, then that means if P then R. So that means that if X is in A, then X is going to be in C. So that means A is a subset of C. Okay. So with subsets, you want to change them into conditionals and then use rules for conditionals to, and logic rules for conditionals to show what you need. Okay. B, you could show with Venn diagrams or with membership tables. All right. C. Okay. Yeah, let's look at C. Okay, so C says if A is a subset of C, so that means that if X is in A, then X is in C. So we change it to a conditional. I think I made that, I did that wrong again. It should be a B. Okay. A is a subset of C. So if X is in A, then X is going to be in C. And we want to prove that A is in the intersection of B and C. Okay, let's see how we can do that. So let's see. So if X is in A, then X is in B. If X is in A, then X is in C. All right, how about if we turn them into not X is in A or X is in B, not X is in A or X is in C. So I change them into disjunctions, and then we want this intersection here. So, oh, okay, I think we can use distribution. Okay, so if we put these together, and not X is in A or X is in C. So basically, if we put these two statements together, then I can see that this is like a distributive law. So this is not X is in A or X is in B and X is in C. Okay. All right. So we can turn that back into a conditional. So X is in A, therefore X is in B and X is in C. This means intersection. So if X is in A, therefore X is in B intersects C. Okay. And this is like a definition of a subset. So if X is in A, then X is in B and C. That means that A is going to be a subset of the intersection of B and C. Okay. So you can see how C works. So yeah, with subsets, you turn them in conditionals and then work with the proposition laws. Then you can prove things with subsets. Okay, yeah, let's look at part E. Okay, so we have A is a subset of B. So that means that if X is in A, then X is in B. All right. Then A cross C as the Cartesian product. So it consists of all the coordinate points. So X is in A and Y is in C. Okay. And let's look at B cross C. Okay, let's see. Okay. All right, so let's see. If X is in A, then X is in B. And I know that we're looking at all pairs of numbers, so X is in A and Y is in C. Okay, so let's see if I can change this into okay, I think I can change this into, that means that, so if X is in A, then X is in B. So I have X is in A, therefore X is going to be in B and Y is in C. Okay, so because this implies that, I can have like this whole set is going to imply that whole set. And this is the Cartesian product of B and C. Okay, so yeah, basically A cross C means all the pairs of numbers where X is in A and Y is in C, but and the Cartesian product B and C means all the X, Y coordinates. So X is in B and Y is in C, but because my X values in this set are a subset of the X value in that set, then this set right here has to be a subset of that set right there. Okay. So I think we can say that if X, Y is a element in A cross C, that implies X, Y is an element in B cross C. So A cross C is a subset of B cross C. All right, I think that's the best I can do for that one. All right, let's see who's around. All right, Tyler. Number 3 for the functions 2 homework. All right, so I'm gonna switch to, actually, I'm going to stop Zoom for a minute or two because I want to record, just save the recording of the session so it doesn't get too long, and I'm gonna log back in about 5 minutes. So if you guys want to stick around and ask more questions, then I'm happy to do that. But I'm going to kick everyone out for a few minutes.